we were doing determination of shape functions for finite elements. First we will take up only elements. So already we have derived the shape function of first order, second order and third order line elements. Already we have derived the shape functions for first order element. They in the natural coordinate system is given by y is equal to -1, y is equal to +1. The shape function is given by 1 minus psi by 2 and 1 plus psi by 2 for first order line elements with 2 nodes. Then we have derived the shape functions for quadratic line element, that is line element with 3 nodes. For this also we have already derived the shape functions. Here it is 0, psi equals -1, psi equals +1, psi is equal to 0. So for this we have derived the shape functions as n1 equals psi into psi -1 by 2 and n2 equals psi plus 1 divided by 2 and n3 as 1 minus psi square. This also we have derived in the previous class. Now we will take up the derivation of the same shape functions by Lagrange formula for 4-noded element, that is cubic element. For cubic element, we will derive the shape functions. So here we have a cubic element, 9 element, 1, 2, 3, 4, 1 and 2 are the end nodes, 3 and 4 are middle nodes, and we will apply the Lagrange formula for finding the shape function. Here, since there are 4 nodes, we have 4 shape functions. The first shape function, n1 is equal to psi minus psi 2, psi into psi minus psi 3 into psi minus psi 4. The coordinates of all other nodes except node 1 we have to substitute and form the numerator, then denominator is psi 1 minus psi 2, psi 1 minus psi 3, psi 1 minus psi 4. This is the Lagrange formula. So substituting the values of say psi 2, psi 3, psi 4, we will get the shape function. Here psi is equal to -1, psi is equal to -1 by 3 at node 3, psi equals to +1 by 3 at node 4, and psi is equal to 1 at node 2. Substituting these coordinates, here I will get z minus z2, that is z minus 1 into psi minus psi 3, that is minus of -1 by 3. Coordinate of 3 is 1 by 3, -1 by 3, and substituting minus of -1 by 3, and psi 4 is equal to 1, that is psi minus 1 divided by psi 1, it is -1, -1, -1, minus of -3, that is +1 by 3, then -1, -1. So if you simplify this, you will get psi minus 1 into, this will be psi plus 1 by 3 or 3 psi plus 1 by 3 into psi minus 1 by 3 into psi minus 1 divided by psi 3 is minus 1 by 3, psi 4 is 1 by 3, psi 2, okay, this is also 1 by 3, psi 4 is 1 by 3, so this is 3 psi minus 1 divided by 3. 3 psi plus 1 into 3 psi minus 1 by 3 divided by, here this is minus 1 minus 1, that is minus 2 into, this is minus 2 by 3, this is minus 1 by 3, minus 1 by 3, that is minus 4 by 3, only this correction. So this is equal to after simplification. So here this 9 is already psi minus psi 2, psi minus psi 3, psi minus psi 4. Here psi 1 minus psi 2, psi 1 minus psi 3, psi 1 minus psi 4. This psi 2 is minus 1, psi 2 is 1, so minus 1, minus of minus 1 by 3, this is minus 1 by 3. Here it is minus 1, minus 1, then minus 1 plus 1 by 3, minus 1, minus 1 by 3. Okay. So this is psi minus 1, 3 psi plus 1 by 3, 3 psi minus 1 by 3, and this is alright. So this is psi minus 1 into 9 psi square minus 1. 3 psi plus 1 into 3 psi minus 1, 9 psi square minus 1, whole thing divided by 9, this divided by, this is 2 to 4, 4, 16, it is minus 16 by 9. So this 9 get cancelled. You have this minus, I will take it up. So it is minus of z minus 1, or that is minus of z minus 1 is 1 by psi into 9 psi square minus 1 divided by 16. This is the first shared function. Then second shared function, N2 on same lines, it is psi minus psi 1 into psi minus psi 3 into psi minus psi 4 divided by psi 2 minus psi 1, psi 2 minus psi 3, psi 2 minus psi 4. Similar to the first one. So this will be psi minus psi 1, that's minus of minus, so it will be psi plus 1, psi minus psi 3, that is psi plus 1 by 3, plus minus of minus, it will be plus. Then psi 4 is psi minus 1 by 3. Psi 4 is 1 by 3, psi minus 1 by 3. This divided by psi Z2 is 1, 1 plus 1, 1 plus 1 by 3, 1 minus 3. This will be Z plus 1 plus I, 1 plus psi. This is 3z plus 1, 3z minus 1. Again it will be 9 psi square minus 1 divided by 9 whole thing divided by. This is 2. This is 4 by 3. And this will be 2 by 3. This reduces to this 9 will cancel. You have complex psi into 9 psi square minus 1 divided by 4 into 2, 8 into 2, 16. This 3 into 3, 9, that 9 is cancels. So this is the change function for node 2. N1 is 1 minus I into 9 psi square minus 1 by 16. N2 is, it is instead of 1 minus I, you have 1 plus I, and this remains there divided by 16. Then N3, N4, that middle shape function for the 4-movement element. N3 is equal to psi minus psi 1, psi minus psi 2, psi minus psi 4 divided by psi 3 minus psi 1, psi 3 minus psi 2, psi 3 minus psi 4. So substitute the value of psi 1, psi 2, psi 3, psi 4. You will get psi 1 is equal to minus 1. So this will be minus of minus 1, which is plus 1. Then psi minus psi 2 is 1. This is psi minus 1. Psi minus psi 4 is 1 by 3. That is psi minus 1 by 3 divided by psi 3. Psi 3 is minus 1 by 3 plus 1 minus 1 by 3 minus 1 then minus 1 by 3 minus 1 by 3. This if you simplify, you will get this is 1 plus xi into xi minus 1 into 3 xi minus 1 divided by 3, whole thing divided by. So this will be minus 2 by 3 plus 2 by 3. This is 3 minus 1, 2 plus 2 by 3 into minus 4 by 3 into minus 2 by 3. So here 3 is denominator 27, here it is 3, so 9, so this will go up, so you have 9 into 1 minus, this is z plus 1, z minus 1, that is z square minus 1, which is 3 y minus 1, whole thing divided by 2, 4, 8 into 16. So this is minus minus plus. So this is the formula 9 plus 16 into z square minus 1 into 3 y minus 1. That is for node 3. On same lines for node 4, the loss shape function, that is psi minus of minus 1, that is plus 1 into xi plus 1 by 3 into the psi Z4 is 1 divided by, here it is Z4 plus 1, Z4 plus Z4 you can substitute straight away is 1 by 3 plus 1. Here also Z4 1 by 3 minus plus 1 by 3 leave to 1 by 3 minus 1. This is for node 1, node 3, node 2. And these are Z4. This is equal to, this is Z plus 1 into Z minus 1, that is Z squared minus 1. This is 3Z plus 1 divided by 3, 4 divided by. So this is 3, this should be 4 by 3 into, this should be 2 by 3, this is minus. So this will be 9, 3, 27, here 3, 9. So this is 9 into Z square minus 1 into this 9 plus 1 divided by, this is 4 into 8 into 16. So that is minus 16. So this will be minus. So all these things make it as 9 into 1 minus Z square into 3Z plus 1 divided by that minus sign and take it inside. So this is the shape function for this cubic line element, one element, cubic line element. There are 4 nodes, 4 shapes. This is for first order element, second order element, or quadratic element. This is cubic element. For all the line elements, that is one-dimensional elements, I have derived the shape function using Lagrange integration function. So this you can remember. If this line lies in y direction, then it's from z to replace it by eta coordinate, eta, and you will get that one. If it is rectangle, 2-dimensional figure, find the tensor multiplication of that. That's the simplest procedure for finding the shape function. Next, we will take up shape function for quadrilateral or the rectangle elements. And finished shape functions for line elements, all first order quadratic and cubic elements. Now we will take up shape functions for rectangular elements. Rectangular elements, 2D elements. First we will take up Lagrange 2D elements. There are 2 types of 2D elements. One is called Lagrange elements, another is called non-Lagrange element. So Lagrange element is applicable for rectangular elements which are very nodes are only lying on the exterior edges. So Lagrange elements. First, say 2D rectangular elements or of 2 kinds. One, Lagrange 2D rectangular elements. are of two types. One is Lagrange type, another serendipity type of 2D elements. In this type of rectangular elements, you will find nodes lying only on the corners or on the sides, on the four sides of the rectangle. Example. Four nodal rectangular element or 8 nodal rectangular element. Rectangle or not 8 nodal, 9 nodal. 9 nodal rectangle element. Where the nodes are symmetric about the center. That's right. And beta axis. The nodes are equally distributed. Here it is 9 nodal. 1, 2, 3, 4. Here 1, 2, 3, 4. And nodes 5, 6, 7, 8, and 9. 9 nodal rectangle. All the nodes are distributed, or it can be rectangular elements like this. 2 nodes in the middle. In the line element you saw, your nodes line only on the edges, then in the middle, and 2 in the line. Same thing in the 2-dimensional rectangular elements. Also, if the nodes are distributed like that, which is beta to the z. Which is 16 nodal rectangle. These are all called Lagrange type of rectangle element, wherein here no middle node, intermediate inside node, here you have one inside node, here you have 4 inside node. If these inner nodes are not there, then it is called serendipity type of element. If the nodes are distributed only on the edges, then it is called serendipity type of element. This is 8 nodal. Eight nodal rectangle. This is a serendipity element, or you can have two nodes on the sides, middle of the sides, like this. Like this. Then nodal rectangle. So these are called serendipity type of 2D elements. For these elements also we can derive the shape function. So for this already I have derived the shape functions. You have n1 is equal to 1 minus psi 1 minus beta divided by 4 for this 4 nodal rectangle. And n2 is given by 1 plus psi into 1 minus beta divided by 4, and n3 is equal to 1 plus psi into 1 plus beta divided by 4, and n4 is equal to 1 minus psi into 1 plus beta divided by which we have derived the Lagrangian function similar to line element. So you can use the Lagrange formula in two directions, take the tensor product. Along this, for node 1, it is 1 minus I by 2. Along node 2, because this node 1 is common for psi as well as theta direction. For this, it is 1 minus I by 2. For this, 1 minus theta by 2. So that is 1 minus I into 1 minus theta divided by 4. That's the tensor product. Same way, to second node here, along the side direction for 1 to element, this is 1 plus I by 2. For this, it is 1 minus theta by 2. So it is 1 plus I into 1 minus theta divided by 4. That's the simplest procedure, like that N3, N4 I have already derived. For this also, I have already derived. Because on side direction as well as theta direction, you have to take the tensor, this Lagrange shape function and take the tensor product. For this also, you can write it as N1 is equal to, along this z direction, there are 3 nodes. For this, you know it is psi into psi minus 1 divided by 2. For this, it is eta into eta minus 1 divided by 2. So this result, net result, I am writing for 9-noded rectangle. The shape functions N1 equals this is psi eta into psi minus 1 into eta minus 1 divided by 4. That is your N1. Along, because this node 1 is common for element 1, 2 as well as 1, 4. 1, 2 is water like element for which shape function is psi into psi minus 1 by 2. Here for 1, 4, this is divided in eta direction for which again the 3 nodes of the element, the shape function is eta minus 1 by 2. This product is this. On same line, N2 you can write it. N2 is equal to the second node or node 1 across the element 1, 2, it is psi into 1 plus psi by 2. For this, it is first node, that is eta into 1 minus eta by 2. So this N2 is given by psi eta into 1 plus psi into 1 minus eta by 4. This is for N2, like that N3, and write it, N3 is equal to, for this, it is second node, psi into 1 plus psi by 2. For this also, it is second node, eta into 1 plus eta by 2. So it is psi eta into 1 plus psi into 1 plus eta by 2. So total is psi eta into 1 plus psi, 1 plus eta by 4. There it is psi eta 1 plus psi, 1 minus eta by 4. And now this for then 4. Then right, this or N2 along that direction is valued to 1 minus psi by 2. Along y direction is beta into 1 plus beta by 2. So that is nothing but sin beta 1 minus psi into 1 plus beta. These are 4 are no shape functions, N1, N2, N3, N4 or even these are here. 4 N2, N3, N4. There is similarities there you can remember. Then middle nodes, N5 N5 also you can write N5, N6, N7, N8. N5, fifth node, it is common for side 1, 2 as well as side 5, 7. For side 1, 2, it is the middle node, that is side direction. So for middle node, 3 node element, the shape function is 1 minus psi square. Just now I wrote that, the second one. You can just see that. Then here, for 5, 7 side, this is the first node along eta direction. Because this is psi direction, this is eta direction. For eta direction is the first node for which shape function is given by sin into z square minus 1 divided by 2. So this next thing we can find is sin into 1 minus sin. Sin is I minus 1 by 2. So this is 3 by 2 into sin minus 1 into 1 minus sin square. So eta direction, eta into eta minus 1, eta into eta minus 1 into 1 minus sin square by 2. This is the shape function for 5th node. In the middle node for side 1, 2, which is along right direction, that is 1 minus sin square, and for eta direction, this is the first node. For first node of 3 node element, shape function is eta into eta minus 1 by 2. So the tensor product of these two is the shape function for 5. On same lines, for N6 is right. For N6, this is second node, that is in the z direction, that is xi is 1 plus xi by 2. Then in the middle node for eta direction, that is 1 minus eta square. For N7, straight away by inspection, you can write it. N7, 7th node, it is common for this 4, 3 side as well as 5, 7. For 5, 7, it is the second node, eta direction. So it is eta into 1 plus eta. For side direction, 4, 3 side, it is 1 minus psi square with node. So likewise, the last N8, 8th node common for 4, 1 as well as 8, 6, 4, 1 is middle node for 4, 1 side, so that is eta direction, so it is 1 minus eta square. Middle node for this is psi direction, it is the first node, that is psi into psi minus 1 by 2. So these are the shape functions for middle nodes N5, N6, N7, and N8. Every case you will find the similarity, you can just try to remember. So this is how you can write with these the shape functions for both 2D rectangular elements as well as 1D objects of elements, like the first order, but as well as like coming to serendipity. Of course, you cannot use this Lagrange shape functions and arrive at this shape function calculation. So you have to just derive from first principle or by inspection. You can just try to remember. By inspection, I would like to give for 8 node rectangular element, the shape of the 8 node rectangular. This is the serendipity. And for eight-noded rectangle element, you can write shape function in the similar fashion. I give you the shape functions straight away. So you can just remember that this for n1 it is given by 1 minus psi 1 minus beta into minus psi minus beta minus 1 divided by 4. Like that you can write for all other nodes n2 is equal to 1 minus psi 1 plus psi 1 minus beta into is psi minus beta plus 1 divided by 4. N3 can write on same lines. N3 is 1 plus psi, 1 plus beta divided by 4. And of course, this will be psi plus beta minus 1 the value. But remember, whatever you have here, then you can write it and another minus 1 or plus 1. Now, this you can use the relationship psi plus beta plus 1 is equal to 0 on this. Because in all these, fundamental property of shape function, that is, sum of the shape functions n1, n2, n3, n4, etc. like that here, that should be always equal to 1. That you can remember. And also, you might be remembering the shape function value here at node 1 is 1 when you substitute coordinates. If you see here, coordinates of 1 are minus 1 and minus 1 here. Psi is minus 1, beta also minus 1. So you will find, if you substitute minus 1 for psi, minus 1 for beta, you will find the value of n1 will become 1. So you see 1 minus of minus 1. If you substitute the values for c, you will get the value of shape function will be always 1. Because 1 minus of minus 1 that is 2, here 1 minus of minus 1, 2, 2 into 2, 4, 4 by 4 is 1. So here no difference is 1. And value of for the same node, if you substitute this coordinates in n2, n3, n4, you will find its value is 0. Because the coordinate function value will be 1 at that node, and value of that shape function for all other nodes will be 0. Similarly, value of n2 for that node is 1, for all other nodes it will be 0. That is a check for you. You can verify all these formula by a check. So here also we are writing that only using that property only. So using that property, you can just write the shape functions directly by this function. Even for 8-noded also, though you cannot apply the time equation, you can write it using that particular fundamental knowledge or property. You can write it satisfying all the property of shape function. That is one important thing. Otherwise, you have to just go from fundamentals, assume a displacement model, and carry out that particular work inversion and the other thing when do it in the head. So for n4, the same line, is equal to 1 minus psi into 1 plus beta, then this will be minus psi plus beta, this divided by. These are the relations for 8-noded 2, 3, you can write this as 1 minus c square into 1 minus beta by 2. Same like then 6, it is 1 minus beta square. You know the beta direction and it is on the z direction. It is at a distance on that side by 2. Then 7, that is this. It will not from z direction, so it is 1 minus z square. It is beta is plus direction from plus beta by 2, and then 8 equal to will not in the beta direction, so it is 1 minus beta square, and z direction is minus 1 minus z. So these are the 4 shape functions for will nodes of the 8-noded rectangle. So like that, whether it is 8-noded or 4-noded, 8-noded, you can write using that property in the case of serendipity elements. In the case of Lagrange element, you can use that Lagrange formula and arrive. Whereas serendipity shortcut method, if you want to adopt, you see the proceeding. Keeping in mind the property of the shape function, that is, sum of the value of the shape function at the node, same node, will be 1, value of the shape functions of all other shape functions at that particular first node is 0. That keeping that particular thing in mind, you can just write the shape functions for serendipity elements also. With this, we have completed the one, that is shape function, both for 2D elements as well as 1D elements. 1D elements you have to remember, so 2D also you can write it in the similar fashion. Now coming to the difference between this Lagrange element as well as the serendipity type of element, the difference, main difference, you can just observe through classical triangle. So we observe that from the classical triangle, these Lagrange elements are superior when compared to serendipity type of element, because each element, Lagrange elements, are complete as well as contingent, whereas serendipity elements will not be complete, and that you can observe by observing this classical triangle. Now I will give the classical triangle for Lagrange elements. For Lagrange element, the classical triangle will look like this. Here 1, x, y, x square, x, y, this is y square, then you have x cube, x square y, x, y square, then you have y cube, then x4, x cube, y, then x square, x, y cube, y to the power of 4. Then you can write x to the power of 5, then x4y, x cube, y square, then x square, y cube, and x, y4, and y5. And like that, with x6 also, here you have x cube, y cube. So this is the line of symmetry. This is line of symmetry. This is x6, this is x5y, this is x4 y square, x2 y cube, this is x cube x square y4, this is x y5, this is x, like that. So you will find that this continuity so you will see this is that triangle, classical triangle. So this is linear element. Then you will find this is what this is for quadratic element, the shape function equation. So this is for cubic equation, cubic element. You see, this is for linear element, all these elements. 1 x, y, x, x, y square, x, y. 1 x, y, x, y. These are the 4 elements which will be present in linear element equations. In quadratic element equations, you will find this triangle. All the elements in this second triangle, that is 1 x, y, x square, x, y, y square, x square, y, x, y square, x square, y square. All these we find. So that is for quadratic element, and this is for cubic element. All the elements in this triangle. It is the third triangle. So you will find these elements are continuous as well as complete. All the elements will be present in the polynomial equation which we select for these elements. So that is why this is called complete as well as it is continuous. Whereas this is for the grand element. So this is the classical triangle. For Lagrange elements, it will look like this. That's correct. Similarly, for serendipity elements, you will find the Pascal triangle is not complete like that. It is not a triangle which is going to be complete. It will be only, it is not complete. It is discontinuous, they say. But in the Pascal triangle, you can see the Pascal triangle is called Pascal triangle or serendipity element. Serendipity elements. So that you will find like that. This is constant linear equation, then quadratic equation, then you have cubic equation, x cube, x square, y, x, y square, y cube. Then you have 4 degree, x4, x cube, y, then x square, y square, then you have x, y cube, then 5 to the power of 4. Then fifth, x to the power of 5, then 4y, then 2y square. They are all fifth degree. Here you have x by 2, then x by 4 by 5. Let's have one more. X to the power of 6, then x by y, x 4 by square, then x2 by 2, so that is symmetric line. Here we will find, you see that linear function, of course, you see that both are linear. So that there is no difference between the Lagrange elements and serendipity elements. But here, with the second quadratic element, there is a change. It will be discontinuous. You will find the elements of the polynomial these two. It will be like this. Quadratic, that is cubic. So there is a discontinuity. We find between these elements. So this, as well as these elements, which are there in the Lagrange element polynomial, you will not find the serendipity type of elements. So this is that mathematical triangle. From this we will clearly observe these elements are superior when compared to serendipity type of elements. Because if you write that polynomial equation for the degrees of freedom as well as nodes, you will find that only these terms are present and it won't be a complete and so functions will not be complete. It satisfies only the geometric similarity. Because the symmetrical, about the line of symmetry, geometric similarity is satisfied, but functions are not complete, but continuous it is there. Continuous and symmetrical. Symmetry maintains, but completeness is not there in the case of serendipity elements. This much information you should remember whenever questions are being write down the difference between Lagrange and serendipity type of elements. That is it. So we have seen the Lagrange finite elements, serendipity type of elements, first order element, quadratic element, cubic element, like that, higher order element, like that, the various types of finite element we saw, and the difference also I have explained between them. Now we will take up altogether different concept called isoparametric element concept. So what is this isoparametric element means? So I will first define what is isoparametric element. An isoparametric coordinate element is, so parametric element is the element, it is the element, the global in which the global coordinates, in which the global coordinates of all the nodes, the global coordinates are expressed, the global coordinates are expressed using the same order, using the same order shape functions, using same order shape functions. Expressed using the same order shape functions, which are used to represent the variation of displacements. For representing the variation of displacements, you have derived the shape functions from the first principles as well as Lagrange shape function and all the formula and all those. So that same functions which you have used mainly to represent the displacement at any point in terms of the nodal displacement, that same shape function you will use to represent the global coordinates that are the displacements in local coordinates. These displacements you have seen in local coordinates, the shape functions used for displacement, there will be local coordinate. There will be local coordinate that you have seen, z eta coordinate. All the shape function formula, just now I wrote, they are all in terms of z and eta coordinate. So that z eta coordinate shape functions you can use for representing the global coordinates of this particular element. And that element, we call it as isoparametric element. For example, if you take the line element, parent element, and quadratic parent element like this, 1, 2, 3, this is the parent element. For this, you have derived the shape functions n1, n2, n3, which n1 is y into y minus 1 by 2, n2 is y into 1 plus y by 2, n3 is 1 minus y square. That you have seen. That same shape functions which you have derived for representing the variation of displacement, if you use it for representing the local coordinates, that is the same shape function, if you use it for global coordinates, the coordinate 1, representation of the coordinate of the node 1, x1, nodal coordinate, if you use it, then the same shape function x1 is equal to n1, x1, n2, x2, n3, x3, like that if you use it, the formula. So if you use like this, x is equal to n1, x1 plus n2, x2, n3, x3. Here you have used to represent the shape function, to represent the displacement at any point, n1, q1, n2, q2, n3, q3, like that displacement at any point, here q1, q2, q3, or the displacement at the nodes if you want to determine the displacement at any point, you can use the shape functions. Displacement at any point Q is given by this formula. Here, if you use the same shape function, whatever you have used to represent the displacement or representing the local coordinates, then that particular resulting element of the transformation, whatever the element shape you are going to get, that we call it as the isoparametric element. That's what we call it. So this element may be of some shape like that. Naturally, it is a distorted type of element. It won't be perfectly straight as the parent element. If you transform that particular thing using the same shape function, the global coordinate, then you get some distorted shape, and that is called, this element is called isoparametric element of this. That's all it is. Like that, suppose if you take what do I do now, the rectangular element like that. So, now then, rectangular element 1, 2, 3, 4. In the natural coordinate, here also this is the natural coordinate. Always in the natural coordinate, center is the origin. So if you take this rectangle element and if you find the shape function, n1, n2, n3, n4, already I have derived. n1 is 1 minus z by into 1 minus beta by 4. Here it is 1 minus a into 1 plus 1 minus beta by 4 like that. So you have already derived this. And that same shape function is using to represent this same rectangle in the local coordinates. If you use the same shape function, the coordinate of this point, here it is minus 1 in local coordinate. Here this will be minus 1, plus 1, minus 1. Here it will be 1, 1. Here it is minus 1. These are the natural coordinates of 1, 2, 3, 4. And we have derived the shape functions n1, n2, n3, n4. So that same shape function, if you use it to represent the coordinates in local coordinates, that is, if you use x equals n1, x1, s, n2, x2, n3, x3, and n4, x4 like that. If you use similarly y coordinate, you can represent it as n1 by 1, n2 by 2, n3 by 3, n4 by 4. So if you use that for any point in natural coordinate, for that particular point it has natural coordinate as sin theta. That can that superpose here and using this to for that particular point the xy coordinate by using this formula to arrive and in transform and plot it like that. The shape what you are going to get is called isoparametric type of element. That is, you are transforming that in natural coordinate global. Like that for coordinate 1, natural coordinates for this, shape functions are, you have that, and if you substitute the global coordinates like this, and if you plot it, then it won't be a rectangle like that, it will be in some distorted fraction. Figure it will be in some distorted fraction, and that will become a quadrilateral. This becomes a quadrilateral. Here also, either it will be distorted shape like that, either linear or curved. Here also it may be, here it is said to be linear. If you go for higher order, it will be curved. So this is called isoparametric. Like that, if you go for the right nodal parent element, like that, then that coordinates, and I have already derived the shape functions to you, and to transform that in global coordinates using the same shape functions, then you get a figure in some kind of distorted shape. Some shape like that. This is called isoparametric element. If you plot it, you find shape like that. This is called isoparametric. It's only a concept. You just use the same equation. You don't go on plotting this, but this is utilized. So this particular concept is helpful in converting from natural coordinate to global coordinates, and all the element properties, mainly the stiffness matrix, we can easily derive using this isoparametric concept, using what is known as Jacobian parameter. Using that Jacobian matrix, we can just derive the stiffness matrix without any problem for all these elements by determining the stress as well as strain, knowing the shape functions. So that we will see in the next class for all problems, that is 2D problem, 1D problem, 3D problem, knowing the shape function of various type of finite elements, how to derive the stiffness matrix equations or stiffness matrix expression for using this isoparametric concept. If I do that, that completes the theory portion of finite element. Only the problems, and once we derive the stiffness matrix, the main element property, both in global as well as local, because this transformation we use for deriving the global stiffness matrix. We go straight away go for this isoparametric concept and derive the Jacobian and use the Jacobian transformation for matrix for arriving at the global stiffness matrix. And that global stiffness matrix for various elements straight away we use in our problems of 1D, 2D and 3D. That's the basic concept of this finite element.